Welcome to this explainer. Today we're diving straight into something that's practically invisible, yet it's completely mind-blowing when you really stop to think about it. We are unpacking the environmental engineering that brings fresh, clean water right into our cities. So, whether you are tackling the environmental engineering syllabus right now, or you're just someone who loves figuring out how the massive infrastructure beneath our feet actually works, you are definitely in the right place. We're going to break down the master planner's blueprint for water supply systems, taking all that complex syllabus data and turning it into a clear, fascinating journey. Seriously, think about it for just a second. What actually happens before you turn on the tap for your morning shower? For us, it feels completely instantaneous, right? You twist a handle and bam, water flows. But behind that split-second convenience is a staggering amount of complex calculation, forecasting, and infrastructure planning. The water coming out of your shower head is basically the final victory in a massive, multi-stage engineering battle against gravity, contamination, and, well, the sheer unpredictable nature of human behavior. To make sense of all this, here is our blueprint for the explainer. First, the anatomy of water supply. Second, the math of thirst. Third, factoring in fire emergencies. Fourth, predicting city populations. And finally, mastering the peak demand. Let's get right into it. Chapter 1. Anatomy of water supply. Before we can even get into the heavy math and forecasting, any successful master plan has to start by tracing the physical journey of a single drop of water. Environmental engineers logically structure a city's water supply scheme into 4 distinct phases. First up is collection. Engineers have to find a natural source and ideally locate it as close to the city as possible to keep costs down. But obviously, just getting the water isn't enough. Step 2 is transportation, which literally means moving millions of gallons of raw water through major conduits. Then we hit step 3, treatment. Surface or groundwater is almost never perfectly safe to drink right out of the gate, so this is where strict purification happens. And finally, step 4 is the distribution network. This is that incredibly flexible system of underground pipes and service reservoirs designed to deliver treated water straight to your house, without interruption even if they're doing maintenance. It's basically a continuous, multi-billion-dollar relay race. Moving right along to Chapter 2, the math of thirst. It's honestly kind of wild to realize that our basic everyday habits completely dictate the size and cost of that massive infrastructure we just talked about. Let's look at how engineers actually quantify this thirst, bringing some standard syllabus data into focus. According to the Indian Standard Guidelines, specifically IS 1172-1993, we use a metric called liters per capita per day, or LPCD. Now, for a standard city equipped with a full flushing system, the absolute minimum domestic consumption is calculated at 200 liters per head per day. That covers everything: drinking, cooking, bathing, flushing. But for economically weaker sections or lower income group colonies, that baseline gets adjusted down to 135 liters per head per day. Knowing these baselines is absolutely crucial, because domestic consumption typically makes up about 50 to 60% of a whole city's water demand. But wait, domestic needs don't tell the whole story. Look at this massive jump up to 500 liters. While a regular household needs around 200 liters per person, a single giant industrial unit, think a paper mill or a massive steel plant, can demand up to 500 liters per head per day. So the moment industrial zoning gets added to a master plan, engineers have to completely overhaul their math. Wet processing industries need vast quantities of water for cooling and manufacturing, which can drastically change the capacity needed for both the source and the entire pipe network. Which brings us to Chapter 3, factoring in fire emergencies. Now, as much as we plan for an average day, true engineering is all about preparing for the worst-case scenario. And in the syllabus, this concept is captured perfectly by a term called coincident draft. It's defined simply as the summation of the maximum daily water demand plus the fire demand. Think about it. A massive city fire isn't going to politely wait for 2 a.m. when everyone's asleep and water usage is low, right? No, it could happen right in the middle of a blazing hot summer afternoon when water demand is literally at its absolute peak. Because of this, the infrastructure has to be heavily proportioned to handle peak everyday use while simultaneously fighting a massive fire. So how do they actually predict the exact amount of water a disaster will need? Engineers rely on some pretty rigorous math for this, specifically models like Kuchling's formula. It looks like this. Q equals 3,182 times the square root of P. In this equation, Q is the total amount of water required in liters per minute, and P is the city's population in thousands. You just plug the population into that formula and bam, environmental engineers get a hard mathematical baseline for the volume of water they need to hold in reserve at all times. But you probably caught the tricky variable in that formula, right? P.
for population. And as we all know, city populations are never, ever static.
And that leads us perfectly into Chapter 4, Predicting City Populations. You know, the water pipes we lay in the ground today have a design lifespan of 30 years or more. That means they have to serve the people of tomorrow. This introduces a really cool type of mathematical fortune telling, population forecasting. Planners use probability models to guess future growth, and two of the biggest ones are the arithmetic increase method and the geometric progression method. The arithmetic method is pretty straightforward. It assumes the population grows at a constant linear rate. It's safe, it's predictable, and it's perfect for older, established cities that can't really expand territorially anymore. But the geometric progression method, that calculates growth at a constant percentage rate, which basically compounds the population over time. This gives you much larger future numbers, making it way more accurate for young, rapidly developing cities that are just expanding aggressively. When you actually map city growth out, you get this really beautiful logistic S-curve. See how the population starts out with this steady growth rate and then suddenly it just accelerates wildly upward? But here's the thing. No city on Earth can grow exponentially forever. Eventually, it hits a physical or economic wall. Notice that point of inflection right in the middle? That's the exact mathematical moment where the city's growth rate hits its absolute peak and begins to slow down. Eventually, the line flattens out entirely at the top, reaching what we call the saturation value, which is the maximum capacity that city can physically hold. Engineers have to map their master plans against this curve to make sure they're building just enough infrastructure at exactly the right time without blowing the budget before the city even hits that saturation point.
Finally, Chapter 5, Mastering the Peak Demand. Okay, so even if we perfectly predict the future population and perfectly calculate the average daily demand, there is one last major hurdle. A city does not drink water evenly. Check out this graph of the hourly rate of water consumption. That dashed line in the middle? That's our calculated average demand. But just look at what actually happens in reality. You've got this massive, huge spike in the morning, between 6 a.m. and 10 a.m., when literally everyone is waking up, taking showers, making coffee, and rushing to work. Then usage totally plummets during the workday, only to spike right back up in the evening when everyone gets home to cook and wash up. It flawlessly maps out our human routine. So the entire system, the pumps, tanks, and reservoirs, has to be engineered not for that safe, flat, dashed line, but to effortlessly absorb those massive peak spikes without anyone's water pressure dropping. It's human behavior, literally dictating the scale of our engineering. So we've walked through the physical journey of a water drop. We've crunched the math for daily thirst and emergency fires, and we've looked at how engineers forecast populations to handle those crazy daily spikes. It is a deeply robust, fascinatingly mathematical system. But I want to leave you with a final, provocative thought to chew on. As our global population completely explodes and climate change keeps altering our natural water sources, can these historical engineering models and master plans really handle the rapid, unpredictable urbanization of tomorrow? It's a massive challenge that the next generation of engineers is going to have to solve. Thank you so much for joining me on this explainer. Keep questioning the world around you, and I'll see you next time.